Okay, this is the calculus Zoom meeting for October 20th, 9 a.m. I think I saw 3 participants, but I don't have it on the screen with your names. Did y'all come out and want to see anything this morning, or just wanted an introduction to this week? Can you all hear me? Now I'm up to 4 participants. Will anybody out there talk to me?
Hey, yeah, we can hear you.
Okay. Y'all just want an introduction to this week?
Yeah, that's fine.
Okay. So yeah, we'll just go through briefly the assignments. Should be a pretty short, straightforward week. Section 9.3 and 9.4. From 9.3, practice problems 3 to 21 and 29 to 37. And for 9.4, I'm just picking out 17 to 33. We'll have quiz 8 on Friday and do Sunday based on these problems. And for WebAssign, 1, 2, 3, 4, 6, and 7, 10 only. And on 9.4, 4, 5, and 6 only. And I believe that's 10 total problems. So just email me the percent of these 10 problems you get correct. 9.3 is our next test of convergence. We're into tests of convergence for infinite series. Maybe I should summarize what we've done. I don't know if that would help. For infinite series. There's the geometric series test. Basically, you have to recognize it is geometric. That would look like a sum of n is 0 to infinity of a r to the n, and it converges r less than 1, and it converges to an a over 1 minus r, and it diverges r greater than or equal to 1. And there was an nth term test for divergence. Basically, you take a limit as n goes to infinity of the terms, and if that's not equal to 0, you can conclude divergence. So we covered those last week. Did anybody want to ask about any of those? Not hearing anything, so no questions. We've got 5 participants now. Nobody wants to ask any questions?
I have a pretty good understanding of last week. I don't have any questions.
Okay, I can't quite hear. You had a good understanding or did not have a good understanding?
I did.
Did, okay. All right, so what happens is 9.3, we're going to continue on. I guess I should, these were from 9.2. Geometric series and nth term test. 9.3, they call it the integral test. And the idea is Take a function positive, continuous, and decreasing. So f is positive, continuous, and decreasing. All right, that word decreasing, these are from 8.8. I don't know if you remember 8.8, but we had 1 over x. We had 1 over x squared, say. 1 over x cubed. These kind of curves. Okay. 4, x greater than or equal to 1, and your an brings up f of n. Then, summation n equals 1 to infinity of the an and integral of f of x dx, either both converge, both diverge. Okay, so see where I get for x greater than or equal to 1, and an comes off of the curve of f of n. All right, I don't know if you remember the results from 8.8. But we took integrals from, say, 1 to infinity of 1 over x dx, and this diverged. We're figuring areas under the curves out to infinity. This one, integral 1 to infinity of 1 over x squared, converged. Same with this one, same. So what they're saying is the series version of this would look like summation n equals, they can run it from, well, I get we'll 1 to infinity of 1 over n. So this looks like 1 over 1 plus 1 over 2 plus 1 over 3. Okay. So what they're doing in 8.8, we had 1 over x. Remember, x is continuous. So you had a continuous curve starting at 1, figuring the area all the way out to infinity. What they're doing is, this where this an is f of n comes from, right here. So at integer points, at 1, you're picking off this dot. At 2, you're picking off that dot. At 3, you're picking off this. You're picking off the integer dots, or dots at integer points, and adding. We'll say dots or values at integer points. So what they're saying is, back in 8.8, we did an integral from 1 to infinity of 1 over x, and I hope you remember that that diverged. I can work it out real quick if you don't remember. Antiderivative is log of x, plug in 1 of infinity. You got log of infinity minus log of 1, which is infinity. Log of infinity is infinity, log of 1 is 0. So there was infinite area under a 1 over x curve, because this did not pinch down hard enough to give you a finite area. Does it not make sense if I pick numbers off and they're not small enough or strong enough to get the convergence for the area? When I pick numbers off, they won't be small enough to add to a finite number. So what they're saying, since I got an infinite area, when I pick numbers off and add them, I pick numbers off and add them, I get an infinite sum. The sum to infinity of 1 over n, because I'm picking these numbers off a curve that diverged, had an infinite area underneath. So when I pick numbers off and add them, this will diverge. Okay, if the numbers do not get close enough to the x-axis to give a finite area, then when I add them up, I'll get an infinite area. I'm sorry, infinite sum. All right, let me pause for station identification before I say do the next example. Any questions about that? Let's just do the next one to contrast it. They'll have you test summation n equals 1 to infinity of 1 over n squared. Now this will look like, they'll say test for convergence. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared. So this will look like 1 plus a quarter plus a ninth plus 1/16. And they'll say perform an integral test. So that means I usually use IT for integral test. I take integral from 1 to infinity of 1 over n squared dn. Okay, now this is where, this is where we test whether you want to get anal or not. If you want to be really hyper technical, I am supposed to switch to x. And use integral 1 to infinity of 1 over x squared dx. Integrals are done on continuous variables, and I'm supposed to use this. But I generally don't. I get sloppy. So I just kind of use the same letter. That bother anybody? Anybody care if anybody out there really anal and want to use x instead of n? Speak up and I'll satisfy your most heartfelt desire and use x. Anybody out there care if we use x or n?
It doesn't matter to me.
Okay. So if you remember, we did this back in 8.8. That's n to the minus 2. You get n to the minus 1, add 1, divide by minus 1. Put in 1 in infinity. So you would get a negative 1 over n, because you switch that back down, 1 in infinity. So you get a negative 1 over infinity minus a negative 1 over 1. Are we going too fast? Which comes out positive 1. So basically what I did was pretended this was a continuous curve, 1 over n squared, 1 over x squared, starting at 1. And you got a finite area of 1, which means this is a strong function and it pinched off to give a finite area of 1, even though the curve technically went out to infinity. So does it not make sense? Sum of 1 over n squared picks off the dots off of a, remember we said this converged. So I'm picking off dots at integer pointers 1 and 2, not 1 square, that's at 2, here's at 3, here's at 4. So I'm picking off the dots at those integer points. When I add them up, does it not make sense that if they're small enough to give you a finite area, they will be small enough to give you a finite sum? So sum of 1 over n squared from 1 to infinity will converge. Does this make sense, or anybody out there going, whoosh, that went way over my head? If they're small enough to give you a finite area, when you do an integral, then they're small enough to add up to a finite sum. If they're too big to give a finite area like 1 over x, then they're too big to add up to a finite sum, and that diverges. Anybody want to ask any questions about this before I try a homework example? This is so awe-inspiring, nobody can speak. Will anybody speak?
I don't have any questions.
No questions. Okay. Well, let's try a homework example then. By the way, this is really the only section in the entire chapter 9 that has anything from Calc 2. In other words, integrals in it. This is the only time we really run into actual integrals in chapter 9. All right, try something off the homework then. (613). I guess we'll try the first one, number 3 of 1 over n plus 3. All right. I don't usually mess around with confirming that your integral test can be applied. I usually just charge right in. Use the integral test to determine convergence or divergence. Did I go through that too fast? Use the integral test to determine convergence or divergence. Okay. If you want to again see what this means, you're looking at 1 over 1 plus 3 plus 1 over 2 plus 3 plus 1 over 3 plus 3, all right, which is 1/4 plus 1/5 plus 1/6 plus blah, blah, blah. The integral test, this is called perform an integral test. Usually write IT for integral test. That means I take an integral, usually whatever, occasionally you'll see 2. There's problems at 1, sometimes 0, but whatever this is, 1 to infinity of 1 over n plus 3. Again, I'm supposed to use x, but I'm sloppy. All right, everybody recognize a straight log of that? Log of n plus 3. Put in 1 and infinity, which gives me a log of infinity add 3 minus log of 1 add 3. Well, that will be infinity add 3, still infinity, log of infinity minus log of 4. And this will equal infinity. Log of 4 is a number, but this is infinity minus whatever that number is still infinity. So this diverges. So here's, you need to draw a conclusion statement. Summation n equals 1 to infinity of 1 over n plus 3 diverges by the integral test. It shouldn't be surprising if 1 over n diverged. You got the same power here. It doesn't matter if you just shifted it basically left by 3, and you'll still diverge. Questions about that?
No, it makes sense.
Okay. We basically, you take an integral of whatever their terms are, from whatever this to this is. Take the antiderivative, plug in infinity in one, work it out. If that's infinite, it diverges. If it's finite, then your series converges. Some of these you're going to have to find formulas for, like on number 9. See how they give you log 2, show it, log 2 over root 2, log 3 over, I'm sorry, number 10, log 2 over 2, log 3 over 3, log 4 over 4. So you're going to have to find a formula before you can do your integral test. Number 9 gives you log 2 over 2, log 3 over 3, add log 4 over 4. Hopefully that's obvious. It would be a sum. I guess I'd started at 2, infinity of log n over n. So there's your log 2 over 2, log 3 over 3, log 4 over 4. You do your integral test would take an integral from 2 to infinity of log n over n, the n. If you want to see that one finished, or 11, you'll have to find a formula for as well. Anybody want to see more examples of that? Okay, there's one other kind of series they show you, and that is P. This is still 9.3 P series. Page 611. Sum n equals 1 to infinity of 1 over n to the p. 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p. So they call this a p series. Okay, so conditions for convergence. If you remember back to 8.8, I'll pull the page up. Won't go through the result. Yeah. If you remember, we showed you this in 8.8. But literally, you're doing an integral test here. And an integral of, I'll write it 1 over x to the p dx came up 1 over p minus 1 for p strictly greater than 1, and it diverged p less than or equal to 1. Hope this hasn't been flushed. So using that, summation n equals 1 to infinity of 1 over n to the p, it will converge p greater than 1. And it will diverge p less than or equal to 1. Okay, if p equals 1, and that's the first kind of example I did, that would give you sum of n equals 1 to infinity 1 over n. P is 1, that's just a straight 1 over n, and that is 1 plus a half, third plus 1/4 plus 1/5. You just get all the fractions added starting with 1. And p equals 1 applies to this. This diverges. If p equals 1, they call it harmonic. It's called harmonic series. I don't know where the name comes from, but they call it harmonic when you're just adding these fractions. We just did sum of n equals 1 to infinity of 1 over n plus 3. This is still harmonic. Okay, you can shift the n anywhere and you'll just shift your fractions. Remember, this started off with 1/4 plus 1/5. You kind of lost the first 3, but it doesn't matter. You're still adding fractions and they still call it harmonic. As long as first power, n first power, first power is considered harmonic and it diverges. Now this is going to be important because later on, next section, we're going to see a variation of this that will converge, and that's where things get very technical and confusing. But this is called a straight, call it with all signs here like this, a straight harmonic series diverges. All right, let's pause for station identification. Anybody want to ask anything about this?
I think we're good. It's pretty straightforward.
Okay. Let me, this gives you a pretty easy P-series test. This gives you an easy P-series test for convergence. All right, so page 613, say number 29. Need to bring that up. If I can get out of that. Let's see if I can get that off. Yeah, okay. So 29 says sum of n equals 1 to infinity of 1 over n to the 7th. Now it's telling you to use the integral test, but I picked off an integral test. But you can recognize this is a P series. You can use multiple tests on same ones. They're all logically consistent. You can recognize this as a P series. The P, that's 7, that power is the P. P is greater than 1, it converges. All right, if I want to be a slave to their directions, the integral test would be integral 1 over n to the 7th, 1 to infinity. You'd have it's n to the negative 7. You'd have n to the negative 6 over negative 6, 1 in infinity. Send that back down, and you'd be at negative 1 over 6 n to the 6. Put in 1 in infinity. So you'd have negative 1 over 6 infinity to the 6 minus negative 1 over 6 times 1 to the 6. You'd come up with 1/6. Because this would be 0. Infinity to a 6 is infinity, and this piece would be 0. So this converges. So they wanted you to do it by integral test, but they gave you a straight P series. The P is greater than 1. That converges. They're all internally consistent. Now, make one point. Again, this gets very technical. You got to be able to recognize a P series from a geometric. Do not confuse P series with geometric. I'll write them to get geometric with geometric. In other words, P series looks like summation 1 over n to the P. N equals 1 to infinity. Geometric look like summation of 0 to infinity of a r to the n. All right. You get the P series has the P is the power, your variable is the base. This is just straight, there's no fractions here. And your R, remember your R was less than 1 for convergence. So your R is the number and your power is the variable. All right, is that as clear as Lake Lanier? Everybody's so awestruck they can't speak. Let me give you one more example, 33, page 613. Test sum of n equals 1 to infinity of 1 over the 5th root of n. All right. They're using, they call it theorem 9.11, but they basically mean the P series theorem. This is a P series. Remember, a 5th root of n could be written as n to a 1/5 power. So this is identical to writing it 1 to infinity of 1 over n to a 1/5 power. So it's a P series. P is 1/5, which is less than 1. It diverges. Questions about that? That pretty much finishes 9.3. Did I hear somebody ask something?
I was just saying it makes sense.
Okay. Is that enough on 9.3? That's pretty much examples out of every section in 9.3. Do you want to see, we're going to briefly hit 9.4. Do you want to see an intro to 9.4?
Sure.
Okay. They give you two tests in 9.4, a direct comparison test we won't mess with, and a limit comparison test. That's the only one we'll do. We won't mess with direct comparison test. Don't thank me all at once. So limit comparison test off page 618. All right. You're basically starting with summation of AN and a summation of BN. All right. And if you take you're basically comparing two series. If you take a limit as n goes to infinity of the AN over BN, and it comes up some number L, if is finite and positive, then AN and summation BN, I'm leaving off the indices just to speak, either both converge or both diverge. So that's what they're saying in this. It's a lot of gibberish. It's not as hard as you make it. The trick is to know what happens with one or the other. Let me show you how it works. They give you a section of these. Okay, so the very first section, I seem to have okay, here we are. Direct comparison test, we're not going to do. The arguments are, yeah, online, I'm not going to do. Okay, so here's where there's using the limit comparison. Here's an entire section of limit comparison tests. And then here is a section of kind of random tests. They want you to figure out which test. They kind of summarize the kind of tests we've done. All right, we've done nth term tests. That was 9.2. I just showed you p-series and integral tests. That was 9.3. About to show you limit comparison. Here, we showed you geometric series. We're not doing direct comparison. I assigned telescoping, but nobody's asked about it. I can show you that if anybody needs it. But yeah, they're kind of doing random tests down here. Let me start in with the first limit comparison, 17. Test summation n equals 1 to infinity of n over n squared plus 1 or convergence or divergence. Use limit comparison test. We very cleverly abbreviate this LCT. Okay. Here's the trick. Let the n go to infinity. So in your terms. Okay, so I take n, take squared, add 1, and let n go to infinity. All right. Well, this will look like n over n squared. You got to imagine what would happen. Don't really put an infinity squared in there. I want to keep my n's, but if I let the n here go to infinity, infinity squared there, it's going to swamp the 1. The 1 will be negligible. I'll keep n over n squared, and I can cancel this, and this will look like 1 over n. All right, well, what I really have is a sum of 1 over n. Okay, now I want to draw a conclusion. Does this converge or diverge? I hope we've convinced you this diverges. It's harmonic. With first power, you can call it harmonic, and therefore it diverges. You also say it's p-series with p equal 1, so it diverges. Keep freezing. Okay, we're back. All right, so now what I want to compare the original with 1 over n, which I know diverges. All right, the book calls them AN and BN. You don't have to keep track of what's the AN, what's the BN. It doesn't really even matter which one you put on top and which one you put on bottom. But for an LCT, you want to take a limit as n goes to infinity. I always put the original over the one you're comparing to. Okay, again, it doesn't matter which one's AN, which one's BN, and I think you could even flip it upside down. You could even put this one on top and this one on bottom. It's very forgiving, but I always do the original over what I'm comparing it to. All right, then to figure this out, limit as n goes to infinity, the n over n squared plus 1 times n over 1. I'm going to flip the bottom. All right, well, that is going to give you limit as n goes to infinity of n squared over n squared add 1. Okay, maybe I should pause for station identification. Anybody want to ask anything? Everybody see where I got this?
Yes, sir.
Okay. So yeah, all you do is form a limit again of the original over what you comparing it to. So this is an infinity over infinity, which brings in L'Hopital's rule. L'Hopital, can you spell it? It's like hospital, but it isn't. L'Hopital's rule. So that would be a limit as n goes to infinity, 2n over 2n. Derivative on top is 2n, derivative on bottom is 2n. N's cancel, in fact, they all cancel, you get 1. This is the L value the book is talking about. And this is where things get tricky. See, we're used to if things come up finite, it always converges. But remember, you compared it to 1 over n, and that diverges. This means my original sum of n equal 1 to infinity of n over n squared plus 1 diverges. Basically because it acts like 1 over n. When the terms go to infinity, in effect, n over n squared, the 1 is negligible, and n over n squared is acting like 1 over n, which we know diverges. So yes, you can get finite results out of a limit, but it actually means it diverges. That's where this stuff gets technical and nasty. Questions about this? That's pretty much all of 9.4. Does anybody, have we opened up your heads important enough today? Or have you got the stomach for one more? No response.
I think that was a lot of information for one day.
A lot of information for one day. Somebody just flashed up a one more. Y'all on the chat line, never check the chat line. I'm not used to this stuff. Chat. Oh, I think this is enough. Okay, so somebody said, I think this is enough. Is that the consensus? All right, so we'll have another Zoom meeting Friday, 9 o'clock. So if you want to ask more about this, other questions that come up. So is this the consensus? Everybody had enough for today? All right, not hearing anything more, we'll go ahead and end the meeting. Appreciate y'all coming out early on a Tuesday morning. Thank you very much.
Thank you.
Thank you.
Thank you.